In the last example, we have used the Pythagoras theorem to show that the orthogonal projection of y onto the subspace of W is the best approximation. And the key reason is this, that y projecting onto the subspace of W resulting in y hat, the error term z is orthogonal to any vectors in W. And because it is orthogonal in any vectors, when we use another vector v to approximate y, it will result in having a right angle triangle. Given that it is a right angle triangle and the shorter side is here, the shorter side is the orthogonal projection, therefore the longer side is this error, and hence by Pythagoras theorem we know that the orthogonal projection gives the best result. The next slides give some links on why the Pythagoras theorems can be extended to higher dimension. We now introduce theorem 10. In theorem 10, our basis is still u1, u2 up to up. However, this time u1 is not only orthogonal, it is octonormal. Basically, it means that the norm of u1, the norm of u2 up to up is all 1. And of course, u1 is still orthogonal to u2, u2 is still orthogonal to u3, and all combinations of them are orthogonal with each other. In this case, we have an octonormal basis. When we have an octonormal basis, equation 2 becomes easier. Let's recap equation 2, where in this example, u1 to up are only orthogonal bases. They are not orthonormal bases. They do not have unit length. However, in octonormal basis, norm of u1 is equals to 1. Therefore, the dot product of u1 with itself, the denominator would be 1 for octonormal basis. This is why all these cancels and equation 2 becomes equation 4 over here. We do not have any more u1.u1 terms in the bottom, u2.u2 terms in the bottom. In other words, we like orthogonal basis, but we like octonormal basis even more because it simplifies how we can find C1, C2, and CP, because we do not need to divide the dot product of ui.ui. This expression over here can be reduced into this expression over here. Let us first write the equation in more compact form. Projection of y onto W is equals to the sum of I equals to 1 to P, y dot ui multiplied by ui. You also can write it in this form, equals to u1, u2, up multiplying by c1, c2, cp. This is the entry of Ci. Now let us figure out how to write equation 5. This term here is u. uty is actually this expression here calculating ci. How do I know this? Well, let us study what is uty. Ut is a P by N matrix. Y is a N by 1 column vector. Therefore, will result in P by 1 column vector. And this is the vector C1 to Cp. In the case when we have P equals to N, that means we have enough columns. In fact, we have all columns that needs to span the Rn space. Then U is a n by n square matrix. And if it is orthonormal, then what happens is that U transpose U transpose times U will also still be equals to I, the identity matrix. And the result is that the projection of Y onto the subspace W, if W is full, then the projection of Y onto W is Y. For the practice problem and the examples given in the next slide, we'll leave it to you to practice. This concludes our discussion on orthogonal decomposition.